Hello and welcome to the second lecture in the series of these amazing, lovely things on audio processing. So in the first one, we've dealt with the concept of linearity and essentially amplitude processing. Now, the natural continuation from that will be to get into many nonlinear options that we have. And as we shall see, these have a collective name, distortion. Actually, it's one of my favorite topics. In fact, I'm an active researcher in this topic. I believe I have invented a fairly successful subharmonic distortion algorithm and other seemingly novel ways of assessing nonlinearities in audio. So let's get straight into it. First of all, in terms of the basic concept or the commonly used meaning of the word, we refer to degradation of signal fidelity or quality. In fact, in some engineering conferences I've presented these bits, the first thing the people would ask is, okay, so how do you get rid of distortion? Not understanding that from a music tech perspective, we are trying to induce interesting types of distortion, whereas engineers typically like to get rid of it. So essentially, early electric blues pioneers, they were the ones who really started using the distortion of electrical circuits and transducers such as speakers, amplifiers, and similar to get a rough distorted quality. Now, distortion itself, what it does, it covers a wide range of changes, mutations of sound, and in many ways what you get in acoustic sources you can call distortion, and typically the process is quite similar. So when you get to drive the system, the acoustical system, very forcefully, then you typically get beyond the linear response, you get into the nonlinear response. So effectively my voice, if I scream, is also distorting in that sense. So it's all over the place, and because it's a basic property of acoustic systems to actually gain stronger, higher spectral components, therefore our appreciation of distortion is also very deep in terms of assessing the character of the sound source. So whereas this set of new spectral components that you get through distorting a source, whereas it would be technically an addition, right, of spectral components, perceptually it is changing the character of. So it is not quite additive like that in terms of perception. And what you can notice is that digital distortions and harmonic distortions, which we will get into, they will typically give you the sense that there is something additional to the original source. So very natural types of distortion will always appear to the listener as if the source has changed and not as if something would have been added to it. So that's an interesting thing to consider when you use distortion creatively, to actually really pay attention to whether this becomes a new sensation or whether it complements or mutates the original source, in fact gives it force, strength, power, presence, everything that is related to a more forceful excitation. Okay, so in electronics, that's where it kind of started making a lot of sense. Amplifiers are typically devices which are linear to a certain degree of amplification, and after that they cannot reproduce the signal faithfully. The quality is degraded. That's the overdrive distortion. So typically when you hit the power rails of the amplifier, so you're trying to produce more voltage than is available from the power supply, and it gets capped. So it is a kind of a clipping thing right there. And then also electroacoustic transducers, like microphones, which transform acoustic energy into electric energy, will distort if the membrane is pushed again beyond the linear region. So typically there is a certain degree, certain level amount of excursion that a membrane can undergo until it hits a hard limit, a physical limit. And if it does, that also becomes a type of distortion, which you can view from two sides, right? So we have said that this distortion can be viewed as a limitation in the actual waveform, be it physical, electronic, or digital indeed. But it can also be viewed as a spectral phenomenon. And these two things are interrelated. So as soon as you have some kind of nonlinearity in the transfer, which we have discussed briefly, you will have spectral components appear. Okay, so similarly, loudspeakers, evidently very often it's the same moving coil mechanism, physical limitations to the excursion of the cone will produce distortion, may it be overdriven. So it is inevitable. That's quite crucial, and what we have discussed last time was a set of dynamics processing algorithms. And even though the nonlinearity undergoes certain smoothing in terms of adhering to the average amplitude, even then the distortion is inevitable, although possibly unnoticeable. Okay, so that's what we're dealing with, nonlinearities, and today we're going to look at nonlinearities, transfer functions that deal with samples. So we kind of went a long way around to get to the simpler bit, because dynamics processing includes an extra component, which means that you could actually use the same type of transfers either sample by sample basis, which is typically your distortion algorithms, or with a certain amount of smoothing in the response, which will give you more of a dynamics process, which actually hopefully makes sense that each dynamic process will induce some distortion, and every distortion will compromise the dynamic range as well. Although there could be situations where the lowest dynamic and the highest dynamic are kind of intact, but typically some kind of warping of the dynamic range will happen. Okay, and this is in contrast to filtering, which I assume you understand, in terms of attenuating or increasing the gain of certain spectral regions. Now we will go into more detail in terms of how a digital filter is built and what it all means a few weeks after this. Okay, so when these spectral components appear, what we can say is that we get a spectrally richer signal, And we can expect a few things. One of them is interference with the actual existing harmonics of the signal. Now, interference, you may know, can be constructive and destructive, which means that the energy at those frequencies can increase or decrease depending on the phase relationships. It is indeed very complex, especially if you're dealing with acoustic sound sources. Unlikely you can predict the type of interference, but you can expect some anomalies in that domain. The other thing that can occur is that the psychoacoustic sensation, so what we actually hear, is also changed due to masking. So masking is a phenomenon whereby typically lower, louder frequencies mask or make inaudible certain softer, higher frequencies if they're sufficiently closely spaced and if the level difference is sufficient for that. And then if the distortion is too harsh, if things are getting out of control or beyond the desired level of intensity, a bit of filtering can do quite a bit. Especially low-pass filtering, you can progressively get rid of those synthesized or produced, I should say, higher spectral components. Now, the main parameter for most distortion is the drive. Most pedals have it. And it is important to understand that this typically controls gain. So drive is just the gain control, but it's gain before nonlinearity. So the main thing about distortion, at least most of the basic distortion algorithms, is that if you push the signal louder into this nonlinearity, it will distort more. You will get more louder spectral components. So this is definitely the most important parameter. Typically, as most distortions do not have a control over the character of distortion. So what you'll, for example, see in guitar pedals, if you have a drive, you might have a tone control, but the tone control is typically a filter. So the nonlinearity itself is very often fixed. And then in digital signal processing, we can go quite a long way in terms of producing variable characters, parametrized characters, such that you have an extra dial to tune the character of the distortion algorithm. And evidently the appreciation of these processes has everything to do with music. As I mentioned, engineers are still likely to strictly avoid distortion, and we are more likely to seek exciting distortions instead. Okay, so let's have some more detail in terms of the origins, which are analog amplification. Evidently, you can imagine, was far from perfect what we had 100 or more years ago in terms of processing signals, electric signals, amplifying them, and all the rest. So the case is that what I've just described is technically called nonlinear distortions. And if you use the term distortion more broadly, then you typically include things that are anomalies otherwise. So things like noise, which is inevitable in electronic circuitry, hiss, hum, these things can also be considered distortion. The bit that we've talked about, the overdrive, but actually there's other types that occur in electronic circuitry, which is the zero crossing or crossover distortions, which is the misalignment of positive and negative signal parts. So certain power amplifiers by design have a different part of the circuit amplifying the positive and the negative side of the signal. And if there is some tuning error in the system, there is a misalignment around the zero crossing when the signal will cross 0 volts. And this is an exciting type of distortion, so we can model that digitally as well. Have a lot of fun with that, hopefully as well. So digital counterpart of amplification, what you see here, is multiplication. scaling. And this is very linear arithmetic operation. It will never produce new spectral components, evidently unless you hit the hard limit of your dynamic range, which in digital signals is typically +1 or -1. And what you often have is that those are the points where the sound card clips, but computationally there is no necessary clipping at +1 or -1. So you can exceed these levels quite a bit internally in your code, in your patch, as long as the final output into the sound card, into the DAC, does not exceed these levels. You should be safe enough. Now, having said that, and trying to be a decent academic, everything that you prove, you try to disprove just as well. So if we are really accurate about this, we have to say that with a finite bit depth digital system, which means that you have a vertical grid for your signal, which is inevitable no matter how fine it is, you will actually produce very little levels of distortion even with scaling. So if you imagine a signal and you try to, amplify it, attenuate it, amplify it, attenuate it, each time you do this, the signal will want to ideally acquire values which are between the grid points. And each time it will be snapping to the grid points. So evidently, if this is a very fine grid, there's not much issue there, but if it's not, there could be. Okay, so what you will often find is that a recording at 16 or 24-bit is audibly different only with very accurate reproduction systems. But if you do a whole lot of digital processing, you slash a lot of effects in chain, then it is likely that you will hear, whether you're doing 16-bit, 24-bit, very often 32-bit, even 64-bit internal processing of the sample values. So the final resolution that goes to the sound card isn't as crucial as this intermediate resolution if you have a stack of digital processes. And the same thing holds for sampling frequency. Okay, so similarly, you need very ideal listening environment to hear the difference between 48K or 96K recording purely through playback. But if you stack a heap of plugins onto these recordings, then at some point the difference shall be audible. Okay, now let's look at the types of distortion from a broader perspective. So not the types of effects in terms of distortion, but the types of distortion in terms of the anomalies that arise. Anomalies, meant in a positive way. First of all, harmonic distortions, right? So this is a set of anomalies, new spectral components that will have a very fixed relationship to the incoming signal. And this is essentially inducing harmonics. This is what happens to acoustic systems. If you overdrive them, they will produce more harmonics. At certain points, new harmonics appear. This is a very natural process in the acoustic environment as well. So typically, clean harmonic distortion is something that you could consider benefits the signal as well. Also, the most basic distortion types, in terms of the types of effects, will produce harmonic distortion. In fact, if you look at electronic systems, it is unavoidable. Speakers, microphones, they will all produce a good amount of harmonic distortion. High-end stuff, not necessarily. Digital processes not necessarily. An interesting class of distortion effect types use Chebyshev polynomials. We won't go deep into this, but it might be interesting to know that typically all the harmonics come together when you distort a signal, but we have a certain set of techniques that allows us to pick out certain harmonics. It is a problematic thing. It works better with synthetic signals. In fact, I have published around this topic as well some better approaches to use to attempting this type of process for acoustical signals. A lot of detail there. We won't go into it. If you catch me in person and you're very interested, I'm happy to elaborate. And then another class of harmonic. Is it harmonic? Is it not? Well, it's subharmonic. In any case, there is a very simple relationship to the incoming signal, but this time you don't get new spectral components above the incoming frequencies. They appear below subharmonic distortions. Typically, people who produce film music, action movie music, they really love their subharmonic processes. You can create a lot of rumble, very, very low frequency sounds from a source that does not contain them, right? So there's new spectral content appearing, and you can do this without any transposing trick or anything similar. Again, slightly beyond the level that we aim at here. If you're interested, I can show you some sources or just quickly go through some of this theory. So those were the bits that produce harmonics and subharmonics. And then we have types of distortion or artifacts, anomalies, that will produce spectral components which do not have this simple relationship to the incoming signal. And therefore they will stand out as a separate signal altogether. Okay, so typically what we're talking about here are intermodulation distortion components. So in this case, the new frequency components that are generated will be the sum and the difference of the existing ones. So when we talk about harmonic distortion and we want to test it, it is sufficient to use a single sine wave and then watch what happens. Do we get more frequencies on top, something below? What happens there? Part of the enharmonic components will also appear with a single sine wave. So this is typically your aliasing, quantization distortion. So when it kind of gets shifted in aliasing, it gets shifted in relation to the Nyquist frequency or the sampling frequency. But with intermodulation distortion, what you get is that you observe it only if you send two sine waves through your process, because then you can observe, okay, I have the A frequency, the B frequency, you will get A plus B frequency, A minus B frequency, and you will get higher order intermodulation components, so 2A plus B, A plus 2B, 2A minus B, 2B minus A. So they spread out quite a bit, depending on the process, and it is one of those things that is not very deeply researched. I mean, in fact, a lot of algorithms that would produce a variety of distortions is something a few of my students went through and actually published some findings which were nowhere to be found. So it is interesting how there is still, maybe not so strongly anymore, but there was definitely a very strong hype around the analog distortions, distortions that circuits produced. And then there was a huge hype around digital modeling of those. And what was left behind was a set of distortions which were inherently digital, whereby the design, the algorithm is such that it's fairly simple to make in the digital domain and rather complex in the analog domain. So there's a whole set of things which is kind of underexplored. In fact, the whole digital signal processing domain still very much relies on the basics of circuitry. So definitely it is the domain which is bound to grow further, stronger, and hopefully in unexpected directions as well. Okay, and then we have what we might classify as intermittent distortions. So these are external disturbances, not necessarily relating to the incoming signal. But in terms of the incoming signal, as I explained, you might get harmonic and subharmonic components or otherwise components which stand out as separate from the original signal, depending on the level. Evidently, you can have harmonic components that are sufficiently loud such that you perceive them as an addition to the original signal, and you can have anharmonic components which are sufficiently soft so they still blend. It really depends on how these bits are arranged. Okay, so let's look into actual algorithms and into the detail of this. Basic first thing you probably heard already, hard clipping. In the digital domain, it looks a bit like the graph in front of you. So what you see is that there is a linear transfer between the input values, right? So input is x-axis, horizontally between 0.5 and minus 0.5. And then if the signal exceeds these values, it gets clipped. So no matter what value comes in between 0.5 and 1 on the output, you can read the y-axis, it will always be 1. Okay, so you see there is the linear domain, and then there is a non-linear bit afterwards. I mean, you could argue that that flat line is quite linear. So the real non-linearity there is the nick right there, and evidently the clipping part will be quite harsh in terms of transforming the signal. Okay, so what you see here in front is a slightly more elaborate transfer function. I've shown you a few last time. They were more sketchy without the values. And the main difference is also that this is a bipolar signal transfer, meaning that the signal has both positive and negative values. And what we've looked at in terms of dynamics processing were typically unipolar transfers, whereby you have only 1/4 from 0 positive values, inputs, positive outputs. So that's also one way of hopefully not getting confused between dynamics processing and actual distortion algorithms. Okay, fairly evident signal clips, that's what you get. It happens in amplifiers that are transistor based. They have fixed output limits, and DA converters have the same thing. Once you exceed the level, that's that, you are distorted. Cool. Here is a little waveform display that shows you how the distortion happens only when the signal exceeds the threshold. So there is our input signal above and the output signal below. So what happens is that we have amplification gain factor 2, which makes it so that the signal exceeds the limits. It is clipped at those limits. So the louder the input, the more distorted it gets. And there is also a sense of having a threshold value, right? A value below which there is no distortion whatsoever. Now, the crucial thing is that hard clipping, basic hard clipping, symmetrical hard clipping, meaning that both thresholds have the same but opposite value, same but opposite. So they will produce only odd harmonics. Okay, so it means if you put in a 100 Hz sine wave, into a hard clipping process. You crank it up, you will get 300 Hertz, 500 Hertz, 700 Hertz, and so forth. You will not get the even harmonics, which would be the 200, 400, and 600. Okay? If you try to visualize that, you might understand that if you really crank it up, you will slowly tend towards getting a square wave, which is what you see in the graph below. Once you amplify it tenfold, it is increasingly looking like a square wave. And you might know that square waves have only odd harmonics. Okay, so these two things can be linked conceptually. Now, through hard clipping, it is not just the odd harmonics. You may get intermodulation components, which you will observe easily if you have two sine waves coming through. You might get some aliasing if the hard clipping is really harsh, if the incoming frequency is really high, then likely some of the harmonics will have passed the Nyquist frequency, the half of the sampling rate, and each one of those that would want to pass it may not, will be reflected back, mirrored back into the audible spectrum, and therefore have an enharmonic relationship to the incoming tone, which can be predicted if you know the Nyquist frequency, which means that running the same distortion algorithm at different sampling rates may produce different timbres. Okay? So that would be your aliasing components, and then it can also suffer from compression. So as you understand, the attacks, the very loud bits in your audio that are distorted, will also suffer from being reduced in amplitude, and therefore you could call this a compression type artifact. The dynamic range will be compromised there. Now, in terms of reducing the aliasing, so if you want your distortion to not have this digital quality to it, by the way, a lot of synths and plugins rely on the characteristic of digital distortion, things like bit crushing, rely on inducing a lot of aliasing artifacts, and that gives them their special character. Just like downsampling, reducing the sample rate. So these types of degradations in terms of the grid of the digital signal have very special character, which is become increasingly more musically meaningful. So in the 80s, 90s, when the analog distortion hype was brewing, no one really thought that these digital glitches could be musically interesting until some artists started using it and new generations embrace it fully, and they seek that type of anomaly, that kind of sound. So times are changing, but if you want to have, let's call it clean distortion, nothing like the digital sounding distortion, yet you are stuck with a digital system, or indeed you like to use the flexibility of it, the speed of, you know, making new things. I mean, by the time you have soldered your design, who knows? Programming is typically much faster like that. Oversampling is the key. So oversampling means that you interpolate between the existing samples, you artificially produce a higher sampling rate, then you do your math, you do your process at this sampling rate, which is typically much higher, 64, sometimes 128 times the sampling frequency. You do your maths there. Once you're done, you can downsample it back to whatever you're used to. And the difference might be obvious. Okay, if you use some harsh distortion, you do it with oversampling, it can actually make a huge difference. And in fact, there is a large set of audio processes that can benefit from oversampling. I've even managed to hear the difference between 64 times oversampling and 128 times oversampling for noise modulation of delay lines, for example. We will get to delay lines. Maybe this example will come up at that stage. Here is the spectral plot of what happens with hard clipping. Maybe difficult to read, maybe difficult to even spot the fact that there is a 250 Hz sine wave just at the bottom of the top graph, one vertical bar, and the rest nice, neat, and empty. And then when you hard clip it, you get all these harmonics popping up. And if you watch really carefully, you might notice that the 250, the original one, evidently stays there. But at 500, which is the first grid line, there is nothing. The next one up is 750. So it's the threefold. So you see that only odd harmonics are being generated with this hard clipping. Here is even harder clipping, and you get this pattern showing in terms of the amplitude of the harmonics. It could be many things. I won't go into this in great detail, but just so you see that in real life, it's not a very smooth decrease. In fact, part of my research went into this type of behavior, which also depends on the input amplitude. And we have hopefully coined the term, which is harmonic instability, for a variety of soft clipping algorithms. Again, distortion is my favorite topic, so it's really I'm really having to scratch the surface only. If you're interested, please approach me. Okay, so what we see here, that indeed harder clipping, louder spectral anomalies. That's what it is. Okay, so let's look at the flowchart for this. So here is the input signal, and then we have first a gain stage, which is typically our drive parameter. And then there could be many ways of depicting the nonlinearity. This display of a clipping function block is one of your options. Evidently, we are asking you to go out there and find flowcharts for interesting audio processes. And there is a variety of approaches there. I may hope that this is one of the more generic ones that might be useful to observe. So what is actually done in code also depends on the coding platform you're using. So in PD and in general programming languages, what we're looking at is an if-then clause. So what we're saying that if the signal exceeds a given level, the threshold, then the signal output will be a given value. If it does not exceed that given level, then the signal output value is the same as the input value, right? So you're defining a linear portion where there is no change to the signal, and then you're defining a threshold above or below which there will be a dramatic difference in terms of the output in relation to the input. Okay, so this type of if-then should be fairly easy to understand. We can do this with the expression tilde, expr tilde object in PD. This is an object that allows you to do all sorts of math. Not the most accessible thing to start with, but definitely very useful to have it in the back of your mind to know that, okay, if I need to do some maths, I can do it by assembling multipliers, additions, and variety of other objects, but actually very often it is more transparent if you use the expression object and just type it out. Now, there is a simpler solution here as well. In PD we have a clip tilde object, easy to use, 2 parameters, upper threshold, lower threshold. This is the one we will start with in the workshop. But good to know that as soon as you want some more nuanced clipping, soft clipping, which we will look at right now, you will need better understanding of maths, and you will need the expression object. So let's look at some soft clipping. I can point you to some papers that try to exhaust the amount of different soft clippings you can come up with. That was part of my brain exercise as a postgrad. And then evidently years later I found out, oh, I've missed one, at least one. So it's like that. It's not very well documented still, I would guess, although these things we've published about 10 years now. In any case, soft clipping relates to magnetic tape saturation, because in contrast to a transistor-based amplifier, it does not stop dead at a certain voltage, but it tries to push it, but it's more and more difficult to get it linear. So there is a very gradual, how should I put it, limitation, right? A gradual limit rather than a hard limit, which you can observe in the transfer function by the fact that there is a curving off that's happening. So at some stage it's not linear, but it's not a really hard knee either. It's a kind of a soft knee, and this will reduce the amount of anomalies, similarly as in dynamics processing, hard knee, soft knee. Soft knees will have less anomalies, but they will also be less snappy, right? So they won't have the response that a harder knee might have. Okay, so basic textbooks on signal processing for audio will typically reference this type of curve, which actually is produced by 3 different stages: linear stage, the curved stage, this shaping bit, and the hard clipping bit. Now what we've discovered is that this is harmonically largely unstable type of soft clipping, which means that depending on the input amplitude, the relationship between the harmonic amplitudes will vary dramatically. So if you were to push a sine wave into this distortion and gradually increase the level of the incoming signal, then the output levels of different harmonics would go up and down like mad. So there are certain soft clipping algorithms that don't suffer from this harmonic instability. And probably the easiest one to implement is this one. This is an arctangent function, which is a trigonometric function, something to do with triangles. I won't bore you with this. But in essence, it's a bit like a sine function. It has a name. You give it an input and it spits out the output. So it doesn't look like a bunch of different operations. It's in fact a single operation. And what you see here, if you look at the detail of this graph, is that there is hardly any truly linear range, but it really curves off very gradually. And what you see is that if you input +1, so if you look at number 1 on the x-axis, then the graph goes up to 0.8 on the y-axis. Okay, so if you input a full level signal that goes between -1 and +1, you will get a slightly softer signal between -0.8 and +0.8. You see, it's fully symmetrical like that. Now, if you exceed the input level and reach 1.5, then you will get about 1 on the output. But actually the property of this function is that there will always be a bit more in terms of allowing you to push it. So it's never truly flat on the top, which means that if you are using this in a digital system, you might want to reduce the output gain just to make sure you don't get to the hard clipping part very soon. But indeed, the nice bit about this one is that you can always push it a bit more. So the amount of pushing you can do, the range of the drive parameter, can be really large. So it is a bit more sophisticated like that. As I said, millions of different algorithms, bits of math you can come up with in order to produce a curve. So essentially any kind of curve you produce, if it vaguely has this shape, it will produce some kind of distortion. In fact, you might ask, why doesn't it curve downwards? And it can do. If you use exponents to produce distortion, you can easily make them curving downward. Again, interesting bits happen. In fact, what you can say is that the curves that curve upward, that bulge like this, they have a kind of compression characteristic to them. And if you produce them the other way around, which have a little trough curving downwards, then they will be an expanding type distortions. So typically those distortions will bring out the attacks and they will reduce the level of the sustained bits. And this type of what you see now, the kind of compressing distortion, will actually push up the background quite a bit and the attacks will be squashed. So depending on what you're trying to achieve, there can be many different things. In fact, a lot of lovely kind of crackly dying off, kind of electronics dying type distortions. At least that's how I describe the sonic character there. Can be done with these. You can also call them gating distortions. So what happens is that when the signal is very soft, it actually disappears altogether. Right, so there's a kind of a gating effect, and as the signal becomes gradually louder, the loudness increases even more dramatically. So you get a very jumpy sort of distortion rather than this squashed type. So millions of things you can come up with here. Very exciting domain, evidently the most exciting for me. And then if you dig into the maths of this, you're looking at more details, you can produce variable knee soft clipping algorithms that'll give you another dial to choose to tune the character of these nonlinearities. Okay, I will gradually speed up, try to squeeze it into 1 hour. Although I was told that 1 hour is a bit much, but for me 2 hours would be probably the ideal duration. But I think I've scratched the surface very well here, I hope. So we'll run a bit faster. Quarter circle distortion, that's actually the one that I left out as a postgrad researching these things. It was nowhere to be found. And then my colleague at UE published a book and he had this one. So the equation here is the equation for a circle, and it's split in two. So the very interesting thing here is that very near the zero, so the softest bits will actually become quite loud, right? So you get a kind of really pushing the soft dynamics, and then the loud dynamics are squashed back again. So it's a kind of a compressing thing from both sides. So it's not just squashing from above, but it's pushing from below. Very harsh type of distortion, really very evidently strong, interesting things to listen to. And then obviously in the workshop we will try and do a few of these, not this one, but I imagine a few of you might get really excited and get into these things. You really don't need much. In fact, a little grapher software that draws out the function is plenty to get you going and get you quite deep. Here is how the waveform looks. Here would be the quiz. We won't go into this. If you like maths, pause the video, ponder, love it. If you don't like the maths, let's get going. Spectrogram of different distortions, clean, hard clip, and quarter circle, just to show you that hard clipping is not the hardest thing. By far not. And then an important chapter here is the asymmetrical clipping. Okay, so as soon as the transfer is asymmetrical, there is a different threshold in positive and negative, and here you have a few different negative ones based on different C values. What you will get is odd harmonics start appearing too. Okay, so this resembles valves, tube amplifiers. This is the waveform that corresponds to that. So unless you have asymmetrical transfer, you will not get even harmonics. And even harmonics are thus associated with the warmer, more analog types of distortion and the rest of it. The worrying thing is that if you do this, you might produce DC offset. So the average value of the signal will be pushed away from zero, which could be harmful to different devices. And this is typically something that you can tackle quite easily with the high-pass filter at a very low frequency. By the way, if you do any kind of audio design production, a high-pass filter at 20-30 Hertz is always pretty much very recommended. A lot of your VSTs will produce energy at those frequencies, which will actually deteriorate the quality and the quality of the bass. So pushing those frequencies with EQs or otherwise is not very recommended. In fact, filtering is what you want to use to omit that. Okay, a bit about the aliasing distortion, right? So that's the one that is reflected of the Nyquist frequency. If there are components that go beyond half the sampling frequency, they will be reflected back. Crucially problematic in certain circumstances. Here's a lovely sketch that shows you how this actually works. So if there is a signal that would be of higher frequency than half the sampling rate, so in the bottom graph you see how very few points are being sampled, and if you reconnect those points you still get a sine wave, but you get a sine wave of much lower frequency. So it's a visual aid to understand why on earth does this happen. Now, in terms of the intermodulation distortion, I've kind of explained this already. Sum and difference components. Here is a sketch of this. So if you have two sine waves, first distorted, then mixed, well, you can try to read this more carefully. There is a 500 Hertz, the leftmost, and then the second loudest one is at number 2, that's your 2 kilohertz. And then you can figure out that the 500 Hertz has 1.5K, then it has 2.5K, and so on. Whereas the 2K, the first one is the 6K, then comes the 10K, and so on. So actually each sine wave has its harmonics, and that's it. So we first distort them and then mix them. But if we do it the other way around, if we first mix them and then distort them, then you will get the intermodulation components. Okay, so typically the first sum component is 2K plus 500, so at 2.5 there is a component, whereas here above, 2.5 was the harmonic of 500, so that's not a fortunate one. But let's say 1.5, is that a more fortunate one? That's not a very fortunate one. 1K is the fortunate one because it appears below and not above. So you can do the thinking here, do the math. And then a few more. So quantization distortion. So this is typically your bit crushing right there. So you reduce the fidelity of the digital signal. That's what happens. We've actually seen the staircase looking transfer last time. And then once you understand, that there's many different types of nonlinearities that you can figure out, implement, all the rest, then it really is down to filtering. Okay, so combination of distortion and filtering is the crucially important thing to look at. And indeed, just as you've seen the mixing before and after distortion is crucially different, in similar ways the filtering before or after distortion will be different. So the question is, how is it different? Okay, pause the video, think about it. So what is the case? If is filtered before distortion or filtered after distortion? So we have one statement which says former has more new spectral components than latter. So former is filtered before. Filtered after has more new spectral components than former, or both have equal amount of new spectral components. Okay, so the filtering is typically the attenuation of spectral components. That might make this an easier decision for you. So they don't just disappear when you filter stuff. You know, you typically have curves, 12 dB per octave. We'll get into the details of that later on. So the point is that if you filter before the distortion, then there will be less spectral components, right? Synthesized, produced. If you filter after, they're still attenuated somewhat, but they're already there. Okay, and then the final thing here, a bit about exciters. You might have heard or used these types of effects already. The legendary oral exciter by Aphex, back in the day when they figured it out, they were renting it per hour with the engineer. So you couldn't buy the box because they knew that once someone gets the box, they will figure out what's inside. And it was the kind of a revolutionary thing that people paid huge amount of money per hour. So some business brains there, not necessarily academic, but very aware of the cash flows. And what they've done is they've made an effect box which made things sound better. Okay, so that was this initial thing. It increases the brightness of the recording without filtering, right? So it's not just pushing certain frequency, but it actually makes the whole signal clearer, more intelligible. They have used it on many ancient recordings, and suddenly where bits were inaudible or not easy to understand, suddenly they become understandable. So what was it? It was subtle amounts of distortion. Okay, so what they've done is they figured out that if the signal is poor, the signal quality is poor, by inducing harmonics which relate to that signal, you're actually making it sound better. So this is a very important thing to figure, that what is distortion for an engineer is necessarily the reduction of fidelity. But already psychoacoustically, so not even musically necessarily, musically everything could go, but psychoacoustically, meaning you can verify it as an objective measure of perception. The case is that subtle amounts of distortion make the signal sound of higher fidelity. Okay, so you have the engineering fidelity and you have the psychoacoustic fidelity, and the two are not the same things. In fact, in certain situations, they're the exact opposite to each other. Okay, so that's this interesting thing to understand about distortion, I would think. And then, I mean, in terms of what they've actually done in this lovely box, I don't know if anyone has had one. I didn't hold one in my hand. I'm not sure if, probably these days, there's a few copies that you can obtain. Not sure if an original box would be something I would pay for. But there were a few other bits in there, typically very careful filtering, some phase shifting, a bit of compression. You know, it was a whole lot of magic, so to speak. But the crucial thing that was not clear to engineers at the time was that subtle distortion can improve the percepted quality of the signal. Okay, well, that's bang on an hour about that. Thanks for your hopeful attention, and I shall catch you soon. Bye bye.